welcome all. Some face that before. My name is Stanley. I'm going to be talking to you about what in the world a weak solution is. So I kind of just wanted to ask, has anyone here in the room actually heard of a weak solution before? Or sort of come across it? Sometimes in passing, awesome. This talk is for a lot of you who haven't. I've tried to sort of come up with how to explain this, literally only trying to use first year calculus at best. So we're going to be working with a lot of really simple examples, things that really only require differentiation in one or at most two variables. And I'll be working with simple ideas, so hopefully some of you don't get sort of too bored by this thing being really straightforward. So, what in the world is a weak solution? So some of you might know about sort of various solutions to differential equations, solutions to PDEs. And the rough principle we get when we go towards talking about weak solutions is that we're trying to think about how do we define a solution for a differential equation where we might actually have a failure of differentiability at somewhere along that solution. So roughly speaking, there are sort of two motivations that I'm going to go through for it, and we have a few sort of nice things along the way to help us. So before I begin, just some rough things on notation. So for all the people who are not sort of familiar with a few things, we're going to often be working with two variable functions, which you will often see me denoting as, say, u, taking inputs of t for time and x for space, and I'm often going to take t belonging to sort of positive time, 0 to infinity, as well as x just belonging to r. So we're going to be working with one spatial variable, so something quite straightforward. I'm also going to denote partial derivatives as follows. Quite often, this sort of the partial subscript t is going to denote a partial derivative with respect to t, as well as the subscript of x is going to denote a partial derivative with respect to x. So for those who haven't done multivariable calculus yet, partial derivatives, just with respect to a variable, just means treating all the other variables as if they were constants. For example, what is the t of whatever t times x squared is? That means deriving with respect to t, treating x as a constant, that's just x squared, and then dx of this is going to be 2tx. That's about the extent of what we need to know. Okay, so the first place we're going to start with sort of the motivation for weak solutions, as well as the whole idea behind distribution theory, which sort of leads into this. Motivation number one is a little story from physics. So, starting out at some point in the 18th century, going on to the sort of all throughout the 18th century, up into the early 19th century, we have a few sort of mathematicians or a few sort of physicists and electrical engineers trying to work with various things in quantum mechanics and signal processing, and they're finding trouble with working with functions that don't quite behave as the functions we know. So, for example, one function that we're going to see a little bit of is one known as the Heaviside function. This is the indicator on the positive real numbers, and it is defined as follows. Heaviside named after Heaviside himself. And this function is going to be 1 whenever x is greater than or equal to 0, and 0 whenever x is strictly less than 0. So we might imagine what it ends up looking like. So if I just plot the function here, it ends up being equal to 1 for the positives and 0 for the negatives. Okay, so quite straightforward. There is this little jump. But the problem is, Heaviside himself wanted to come up with a notion for the derivative of what this function would be. And a lot of you would know the derivative seems kind of okay to calculate, except when you start to look at 0 when we're starting to get a problem. But sort of ignoring that fact, ignoring sort of the failure of continuity at that point, let's go ahead and see if we can find it. And this is what was sort of denoted by Dirac as the delta function. And I say function in quotation marks because it's not quite a function. We'll get to why. But Dirac comes up with this idea. We say, let's suppose this delta function, often known as the Dirac delta, is precisely the derivative of the Heaviside function. Okay? And so what are its essential properties going to be? One, the first property is, just looking at how the graph is flat, the first thing we're going to look for is the fact that our function, our delta function, needs to be 0 whenever x is not equal to 0. Okay? That's a really, I think, natural thing to pose. We want it to be 0 whenever x is not 0, At 0, we don't quite care. Awesome. The other thing, and this is where we sort of end up with some problems, is let's suppose we need to satisfy, in order to be the derivative, we need to be able to integrate that as a function. So let's suppose we want to calculate the integral from essentially minus epsilon to epsilon. So we're just going to go, epsilon is something positive, and we're just going to ask for that derivative over the interval. We're going to eventually stretch that out to infinity, but let's suppose we can use the fundamental theorem of calculus. Now the problem is we can't. The Heaviside function has a discontinuity, the fundamental theorem doesn't work. But if we proceed anyway, what are we expected to get? Well, if I integrate sort of formally, I'm really integrating the derivative of the Heaviside function. The Heaviside function was then going to be, by the fundamental theorem of calculus, FCT, we're going to the Heaviside function of epsilon minus the Heaviside function of negative epsilon, which is what? At positive epsilon, it's 1, and at negative epsilon, it's going to be 0. Okay, so it turns out it should be equal to 1, and then we end up with a situation where the integral, if we take epsilon to infinity, that should pose no problem, but we should get that the delta function has an integral from minus infinity to infinity of 1. Yet it is equal to 0 everywhere when x is not equal to 0. So, under the theory of Lebesgue integration, this essentially poses a problem. Delta cannot be a function because it is almost everywhere 0, so the function needs to be almost everywhere identical to 0, and therefore have a sort of an integral of 0 from minus infinity to infinity, not 1. So sort of reconciling the fact that the integral needs to be 1, but the derivative is almost everywhere 0 is a problem. We can't ever get a function. So part of distribution theory is to try to answer this question, or give us a theory which can actually sort of do that. The second place, and this is where we're going to introduce the idea of a weak solution, is essentially trying to deal with equations which sort of sound very physically. So these are differential equations which describe something in nature that make a lot of sense, but the equation, the solution that we're looking at has problems of differentiability. So to do that, I'm going to take a look at a specific example. We're going to look at the wave equation. And this is going to be the wave equation in one dimension. So we're going to look at solutions, taking variables in time and space, which are continuous. Okay? So they're continuous on the time and space. And the equation that we're sort of looking at is going to be the following. It's going to be 2 time derivatives of u minus 2 spatial derivatives of u need to be equal to 0. Okay? And so what this is known as, this is the wave equation, and basically it gives any equation, anything satisfying this equation sort of describes a traveling sort of wave on one line. So for example, I might pose sort of here an example where you say like the sine wave, if there is, or maybe say sort of something like a bump, and as the bump essentially travels this way, if it's a continuous bump, that would be something which satisfies the wave equation quite nicely. So it starts at some the profile starts at some point, you increase time, it sort of slides on. So what would be a very natural solution that ends up having some forms of non-differentiability? I'm going to go to signal processing or sort of electronic music for this, and I am just going to show you the following. So it comes up. Okay, basic waveforms. And we can actually hear a few of these sounds of various things. Okay? We can hear some tones. Let me find what I find. This is the square wave, and then this here is the sawtooth wave. Okay? So the sawtooth wave, see if I can find another good video. Sounds something like this.
Yeah, this is the sawtooth wave?
Yeah. So this is if they can. And so in terms of electronic music production, pretty popular if you want something like really crunchy, really textured. I'm not going to get to that. But here, if you wanted to take a look at something of what the sawtooth wave might look like traveling, I've created a little Desmos animation here, right? It's these sort of straight lines that drop off infinitely. And just sort of imagine as time goes forward, it's as t, this is on x, and as t increases, the wave sort of slides to the side. So it's sort of periodic, but it's going to be jagged at all of those corners where the wave is starting to fall off. Okay? And that's going to pose a problem. So if we return here, okay, I have a situation where the wave equation I want the wave equation to work for something like the sawtooth wave. It's something which I can imagine very naturally, it appears somewhere, but the problem is at all these sort of points at regular intervals, I'm having this issue of differentiability. Because what happens is, because I have those sharp points, I end up taking a look at the time derivative and taking a look at the space derivative at those points, and it fails to exist. So one answer I could do to this is to totally ignore the problem. I could say, all right, well, my sawtooth wave seems to work at almost every point in the interval, and I'm just going to take that as valid and just totally ignore the fact that I have differentiability problems at all these places. That would be fine, but that is not an answer we're looking for. So the idea behind distribution theory, and certainly the idea behind a weak solution, is to give us something which is regular and consistent in terms of answering that, something where it is we can get a good answer to this question that is totally unambiguous. So how do we actually get started with building a weak solution? We can actually introduce kind of the idea of a weak solution without looking at distribution theory. And the way I would do it is to essentially take this equation and essentially say, look, let's suppose we take some function, I'm going to want this, we take some function, I'm going to call this phi, taking variables in t and x, and I'm going to say this is nice. So this is a pretty nice function. And what properties do I mean by nice? Well, the first thing I want is I want this function to be infinitely differentiable. So I want to take a function which is infinitely differentiable, and the other function I want to take, I want to vanish on the boundaries. Okay. So the other property I want is I want my function phi to go to 0 when I take sort of my x variable, my space variable to the infinity, when my time is 0 or t. So that might be a nice starting point. And what I'm going to do is I'm going to essentially take my function phi, and I'm actually going to multiply my equation, or my wave equation, right, by this function phi. Okay? So if my wave equation holds for you, I can multiply it, and that would be nice. And then I'm basically going to integrate across my two variables. So that's going to look something like this. So integral 0 to infinity of phi tx t dx t, and then I'm going to same thing here. Okay. And essentially this, if I integrate this expression above, this is going to be the same as integrating 0. So I would expect that the sort of the difference between these two integrals is equal to 0. And here what I've done is I've converted my differential equation really into an integral equation I want this to satisfy. And next, sort of kind of being a formal trick, if phi is really nice, I can essentially do integration by parts on something like this. So if I apply integration by parts, I'm going to move one of the t derivatives over to the phi. So what's that going to look like? Well, in terms of doing integration by parts, the first thing that's going to happen is my uv term in the classical formula is going to be 0 because I've taken my phi to be very nice in that it vanishes on the boundary, so it disappears. Then, after my integration by parts, I'm going to look at and end up with the time derivative of phi, and then on the u is only going to be a single time derivative as well. Okay? So this whole thing is equal to 0 minus this integral. And then I'm going to move the other t over again. So I'm going to do that again. That ends up being another 0, so it cancels with the, I get the negative cancel, and I essentially end up with utx, 2 time derivatives on phi, 2 time derivatives on phi instead. So I've migrated my differentiation from my function u, which should be my solution, and essentially put it on my really nice function phi. So I can actually do the exact same thing here. So I do same thing, and I end up with something a little different. The overall equation I end up with looks something a little like this. 0 to infinity over r utx dtt phi tx dxt equals to 0. And here what can I see? I can see that my u's are no longer being sort of differentiated, and instead I've got derivatives on my phi. And I essentially say the following. If u is such that should be two words, such that isn't a single word, is such that this thing here, this equation, which I have asterisks, holds for all nice sort of possible functions phi, then u is a weak solution to the wave equation. Awesome. So what has actually gone on? If I return to my original equation and I say I have a solution to this, this differential equation, which is here, I actually need that, in order to make sense at every single point, I need that differential equation to be twice differentiable at every point tx. So I need to be able to take 2 time derivatives, I need to be able to take 2 space derivatives. Okay? And that poses the problem, because something like the Saw wave does not have that differentiability at those points. So how can I fix that? Well, if I pretend that my u does have that differentiability, I can actually make all the following steps. Okay? And I say for any nice function, this should hold and this should hold. Okay? And I essentially change the equation to look like this. Only thing is, by shifting the form from a differential equation to an integral equation, I actually don't need the same a priori data. What I mean by that is that integral equation, which is up there, is now able to hold true for u just being continuous. I don't actually need to assume any differentiability because I'm not imposing something like a differentiability. I'm not sort of differentiating the term. If u works and solves that equation, here it is a weak solution in that if it is also a solution of this equation, originally it holds, but it is now possible to get solutions of this integral equation, like the sawtooth wave, which don't satisfy the equation before. And that, in essence, is the idea of a weak solution. We have changed it from the differential form to an integral form, thereby weakening a lot of the differentiability conditions we need on it. And that's how we can sort of think of it starting to expand calculus. So, I'm going to skip over a direct example of a weak solution. And so this gives us enough to try to motivate the idea of what a distribution is. So the first thing I'm going to do is ask, well, this answer, what is the nice enough functions we're going to work with? Okay? So we're going to try and define what are those nice functions, and this time I'm going to define nice functions on just the real numbers, just on R. So you might have noticed earlier when I was walking through the weak solutions to the wave equation, I was working on nice functions defined on time as well as space. For the next small section, I'm going to work just on distributions defined on R because it's a little easier. So, what are the 2 properties we need? The properties we seem to want, are the following. We wanted it to be smooth. Okay? So we need it to be infinitely differentiable. Okay? And the reason why is that when I'm sort of looking at differential equations, I want to be able to move however many orders of differentiation over onto my nice function. That's why I need it to be infinitely differentiable. The other thing I need is at least it has to vanish on the boundaries. So in terms of doing integration by parts, that UV term that comes out, I don't want that to be apparent, or I don't want that to be there. So by forcing it to vanish on the boundaries, I actually keep my intervals nice, tight, and clean. So what is the test functions, or what can I work with? I'm going to define now the space of test functions. And I'm going to call these test functions because they're something like, they feel something like a measurement function as the continuous functions which are infinitely differentiable and they are also supported on compact sets. Okay? So this is going to be smooth, meaning infinitely differentiable, and compactly supported. Compactly supported is terminology some of you might not have heard of. It means the function is non-zero on a finite interval. That's what compactly supported means. So an example of a test function that we're going to see, and the classic example is going to be the following. It's going to be phi x is going to be defined as the exponential of 1 over x squared minus 1 whenever x is, the absolute of x is less than 1, and it's going to be 0 elsewise. So this function is going to look a little like this. If I draw it out, so it's going here, it's minus 1. My function. It's going to look a bit like this. So it's a sort of very smooth bubble. And this is an explicit example. I've written out as a test function, but for the most part, we're not going to write down many test functions. Test functions are really easy to draw and imagine, but actually writing them down with the smoothness and the compactly supportedness as piecewise expression is kind of annoying. But largely speaking, we're just working with this space. And these are going to be my collection of nice functions. So this brings us to, I guess, one of the big elephants in the room, which is what is a distribution, if you might have heard of it. So a distribution, which I'm going to find, the space of distributions is going to be equal to the space, to the continuous, and continuous in this case is going to be equivalent to bounded, the continuous linear functionals on my space of test functions. Okay, so what do I mean by continuous linear functionals? So I'm going to denote this space with essentially this sort of calligraphic D dash, and it's going to be defined on. So by continuous linear functionals, I mean that if I have a functional, which I'm going to call capital T, in my space of distributions, then what happens is my T should essentially take as an input to the functional a test function. So I should essentially be inputting test functions, and then as an output, I should be getting something that is a real number. And the sort of the properties that we enforce are we require the functional to be continuous, and we also require the functional to be linear. The property of continuity is actually kind of tricky and dicey. It has to deal with a lot in terms of topologies on the space of test function and distributions. In this talk, I'm going to actually ignore sort of discussion of their topologies because it is quite tricky, and we can capture a lot of the other ideas. But things of convergence, matters of convergence, are sort of going to stay up in the air for a while. A classical derivative there. It does, however, have a weak derivative. The weak derivative, which I'm going to call G, of the absolute value function is given by 1 if x is greater than 0, minus 1 if x is less than 0, and it turns out almost quite nicely and quite expectedly, a possible good weak derivative is 0 when x is equal to 0. And that will be a derivative which holds weakly. However, we end up with another problem. For example, something like the Heaviside function that I defined earlier has no weak derivative. So it turns out it is not possible to find a single function g which can be the weak derivative of the Heaviside function. But that's okay, because the weak derivative and its behavior at these four functions gives us an idea on how we define the derivative of a distribution. So let's now move on to defining the distributional derivative. So if I recall the following, let's say I'm looking with a function which is f, right? Then the distribution for the derivative of f phi would look like this. It is the inner product f phi tested against the test function, which is integral f dash x dx. So this is here, this works for f differential. So I can differentiate f, then its corresponding distribution is as follows. So what is this equal to? This one here is equal to, after integration by parts, again with the vanishing first term, move the derivative onto the test function like I am doing with the weak derivatives, like I am doing the weak solutions, and I essentially end up with something which looks like testing the function f against the negative derivative of the test function. Okay? That in principle is the way we go about defining the derivative of a distribution. So this is what is done by Schwartz when he actually, somewhere in the 1930s and 40s, when he defined this. The distributional derivative is defined as follows. If I have t a distribution, then the derivative, which I'm going to, or the derivative, or the first derivative of this, is going to be defined by negative of the distribution, and I take the first derivative of the function I test on. So that's how I actually define the distributional derivative. And you can see how that's actually consistent for the functions, consistent for everything before. And this actually gives me a good way to now talk about nth order derivatives of the pattern, because if I now take the nth order distributional derivative, that just ends up following the pattern being quite recursive. Minus 1 to the n, t, my distribution, and then I take the nth order derivative of my test function. Okay? And now, this actually solves my problem. So, if I return to trying to find the derivative of the Heaviside function, that is evaluating the first derivative of the distribution corresponding to the Heaviside function, this is going to be equal to negative the distribution corresponding to the Heaviside function, and I'm looking at the first derivative of my test function. Writing that out in its integral form, that is integral over r of the Heaviside function, and then I'm looking at phi dash of x dx. Okay? And now, what's going to happen here is, what is my Heaviside function? My Heaviside function is 0 from minus infinity to 0, and then 1 from 0 to x. This integral is merely minus 0 to infinity of phi dash x dx. And with some rough calculations, phi infinity minus phi 0. And because phi vanishes, this becomes 0, and I end up with phi 0, which I might remember was actually my delta function, or my delta distribution, evaluated the same test function, phi. Right? So here, I get that the delta function, or the delta distribution, I might say, is distributional derivative of my Heaviside function, thereby fixing essentially, or making rigorous, the problem of Heaviside and Dirac that I first learned. Okay. So, I had a few more examples of distributional derivatives to go, but we're running a little short on time, so I'm going to keep moving forward. And we can now take a look at, now having introduced the idea of distributions, trying to solve a few equations in distributions. So, solving equations. Okay, so let's take a look at one example to start with. Let's suppose I wanted to solve sort of x times u, where u is at least a function of x. Okay, when I work in distributions, u is not going to be required to be a function of x, but let's suppose I tried to solve this. Okay? It turns out the only solution to x times u being equal to 0 for every x is u being identically 0. Okay? This is the only solution for u, and sort of that is locally integral. Okay? Is u is identically 0. But if I extend this to distributions, what I get is the following. allowing distributions, I get that u equals to any constant times the delta distribution, which I'm denoting here as a function. Denoting here as a function, we often see that sort of double up. Sometimes it really isn't a problem. Is a solution which is a distribution. Okay? And to verify that that is the case, well, what happens? When x is not equal to 0, my equation is 0 times my delta distribution slash function, which is 0. And when it is equal to that, no, not that, sorry, my bad. It's the other way around. It's equal to a classical derivative. It does, however, have a weak derivative. The weak derivative, which I'm going to call g, of the absolute value function is given by 1 if x is greater than 0, minus 1 if x is less than 0, and it turns out almost quite nicely and quite expectedly, a possible good weak derivative is 0 when x is equal to 0. And that will be a derivative which holds weakly. However, we end up with another problem. For example, something like the Heaviside function that I defined earlier has no weak derivative. So it turns out it is not possible to find a single function g which can be the weak derivative of the Heaviside function. But that's okay, because the weak derivative and its behavior, at least for functions, gives us an idea on how we define the derivative of a distribution. So let's now move on to defining the distributional derivative. So if I recall the following, let's say I'm working with a function which is f, right? Then the distribution for the derivative of f phi would look like this. It is the inner product f phi tested against the test function, which is integral f dash x dx. So this is here, this works for f differentiable. So I can differentiate f, then its corresponding distribution is as follows. So what is this equal to? This one here is equal to, after integration by parts, again with the vanishing first term, move the derivative onto the test function like I am doing with the weak derivatives, like I am doing the weak solutions, and I essentially end up with something which looks like testing the function f against the negative derivative of the test function. Okay? That in principle is the way we go about defining the derivative of a distribution. So this is what is done by Schwartz when he actually, somewhere in the 1930s and 40s, when he defined this. The distributional derivative is defined as follows. If I have t a distribution, then the derivative, which I'm going to, or the derivative, or the first derivative of this, is going to be defined by negative of the distribution, and I take the first derivative of the function I test on. So that's how I actually define the distributional derivative. And you can see how that's actually consistent for the functions, consistent for everything before. And this actually gives me a good way to now talk about nth order derivatives of the pattern, because if I now take the nth order distributional derivative, that just ends up following the pattern being quite recursive. Minus 1 to the n, t, my distribution, and then I take the nth order derivative of my test function. Okay? And now, this actually solves my problem. So, if I return to trying to find the derivative of the Heaviside function, that is evaluating the first derivative of the distribution corresponding to the Heaviside function, this is going to be equal to negative the distribution corresponding to the Heaviside function, and I'm looking at the first derivative of my test function. Writing that out in its integral form, that is integral over r of the Heaviside function, and then I'm looking at phi dash of x dx. Okay? And now, what's going to happen here is, what is my Heaviside function? My Heaviside function is 0 from minus infinity to 0, and then 1 from 0 to x. This integral is merely minus 0 to infinity of phi dash x dx. And with some rough calculations, phi infinity minus phi 0. And because phi vanishes, this becomes 0, and I end up with phi 0, which I might remember was actually my delta function, or my delta distribution, evaluated the same test function, phi. Right? So here, I get that the delta function, or the delta distribution, I might say, is distributional derivative of my Heaviside function, thereby fixing essentially, or making rigorous the problem of Heaviside and Dirac that I first learned. Okay. So, I had a few more examples of distributional derivatives to go, but we're running a little short on time, so I'm going to keep moving forward. And we can now take a look at, now having introduced the idea of distributions, trying to solve a few equations in distributions. So, solving equations. Okay, so let's take a look at one example to start. Let's suppose I wanted to solve sort of x times u, where u is at least a function of x. Okay, when I work in distributions, u is not going to be required to be a function of x, but let's suppose I tried to solve this. Okay. It turns out the only solution to x times u being equal to 0 for every x is u being identically 0. Okay? This is the only solution for u and sort of that is locally integral. Okay? Is u is identically 0. But if I extend this to distributions, what I get is the following. Allowing distributions, I get that u equals to any constant times the delta distribution, which I'm denoting here as a function. Denoting here as a function, we often see that sort of double up. Sometimes it really isn't a problem. Is a solution which is a distribution. Okay? And to verify that that is the case, well, what happens? When x is not equal to 0, my equation is 0 times my delta distribution slash function, which is 0. And is equal to that? No, not that, sorry, my bad. It's the other way around. It's equal to